Hmm. All right, everybody's coming in at one time. I'll be right back. Hot. Good morning, everybody. It's Monday, and as far as I'm concerned, it's about the last Monday. We'll see. While we're waiting, does anybody have any questions on anything? I know you've been working hard on the test this weekend, so when you can get those, I don't know if I said today before class or just today before 5. I can't remember. Did anybody remember what I said? Did I say before class or before 5?
I think you said before 5.
Okay, that's fine. All right, that's good. That's what I sort of thought I extended it, but I wasn't sure until after class. So, let me get my screen up. There are a couple things I want to talk about while people are coming in, and it's sort of like to look at a kind of a plan for the rest of the semester. I've really only got one more major topic to do, and I expect to finish that up probably Friday. Maybe just wrap up loose ends on Monday. But we'll talk about what we're going to do for various things like final exams and things like that. Let's see, who have I got so far? Allison, Brittany, Christina, Ella, Jessica, Sylvia. All right, let me get my screen up here. All right. So, so guys, I've put this on Moodle. It's pretty much our last assignment sheet. There are a couple of things that might change on it, but not much. Today, I'm gonna do one more systems problem, one we kind of started off systems with, and I wanted to finish it up. I'll then, the last topic I want to do is springs. So, and that's just an application of systems of linear DEs with constant coefficients. So they won't be hard to solve, but there's a fair amount of physics we've got to do to kind of facilitate that. But I'll make it easy in terms of the physics, I hope. Let's see, there's Saron. So I want to know, and I can't see everybody because I've got some video cameras that aren't working. I'll let you unmic and tell me. Ella, have you ever had a physics course?
Yeah.
Okay, all right. In high school or in college?
Both.
Okay, all right, good. Sylvia, physics course?
No.
No? It's okay. It's all right.
No.
So if I ask you what Newton's second law of motion is now, you're gonna you're kidding, right? Yeah, so we'll go through all that, okay? Saron, have you had a physics course?
Yeah, I have.
Okay, in college?
Yes.
Okay. Allison, have you had a physics course?
Yes, in college.
Okay, good. Christina, have you had a physics course?
Yeah, I had one a long time ago in high school.
Okay, all right, that's good. I mean, it's just basic physics. We're gonna be talking about springs, but Jessica, physics course?
Yes, in college.
Okay, all right. So you took physics at Salem?
Yes.
Okay, good. Who didn't I ask? Jessica, Allison, Christina, Ella, Jessica, Saron, Sylvia. Okay, I think I got everybody, and I don't think anybody's waiting in the waiting room. Anyway, we're just going to do some problems with physics. Well, I mean, with springs, which is a little bit of physics. But once we get the systems set up, the systems are not real hard to solve because they're just linear equations with constant coefficients, which we know a lot about. So today I want to finish up the tank problem that we started initially, we started systems of equations with initially. I wanted to introduce the springs as much time as I have. There's not much homework at all. I'm sure I will not get past anything from problem 1 on 205. So it's really not a whole lot of homework tonight. there is an assignment due Wednesday, but I sort of pared it down. I got a 2x2 system right there, so we don't sort of forget that. The two things that we will not have had a test on will be systems and the spring stuff, but I'll figure out what to do about that. But so there's one. We had two methods. We had the elimination method and we had the determinant method. So that one shouldn't be too bad. It's non-homogeneous. You can use either method you want. Doesn't matter to me. We had a couple of different kind of substitution problems. I put one of those on there. I typed them on there. They are problems. This one, at least I know is a problem in the book. I'm not sure exactly where I got that one, but I've typed them on there so everybody has access to them and doesn't have to worry about what page it really is on. After that, on Wednesday, we'll continue to do springs, and then on Friday, we'll do more springs. There are three types of spring problems we want to look at. We want to look at damped motion, undamped motion, and what's called driven motion. So those are my last topics. Now, as far as the final exam goes, here's what I'm thinking about doing for the final exam. Some of you have opted for a pass, no credit. Some of you have opted for a grade. If we get to the end of the homework and whatever I'm going to do with springs and systems, and you're happy with your grade, I'm not going to require you to take a final exam. Okay. If you're not, and I will have the grades ready for you and talk to you about what you've got next week before finals start, then what I'll do is I'll give you a comprehensive final, and you can replace your lowest test grade with your grade on the final. Okay, there won't be any penalty if you don't make as high on that as you have on your lowest test grade. Hopefully that's not going to be the case, because this now will be open book, open note, whereas the first half of the semester was not. So I hope that sort of makes that better. You can take the comprehensive final, but again, if you want to replace a lower test grade with that, I'll have your homework. We've got well over 100 problems already, 100 problem points in homework. That's going to count a test grade, and most people doing okay on that. So that's what I'm thinking about right now. It's been kind of a slog. This half of the semester is different for all of us, and I feel completely justified in doing that for the final exam, and maybe as a way to help people that have a low grade, and a way to relieve a little bit the ones that are just happy with what you got. Okay, which in some cases is very good. Okay, so you make questions about that? Anybody problems or questions? We okay with that? All right. So let's go and look at one more systems of equations problem. That's not what I wanted right there, and that's not what I wanted right there. Let's see. Let's try this one. Nope, that's not what I want. That's what I want. Okay. So I'm going to go back to the problem we started off talking about systems of equations with. We never solved this problem. So I want us to look at it. I want us to solve it. And then I'm going to try some graphing online to look at what actually happens with the problem. We had two tanks. The problem was there was pure water flowing into one tank, and then out of another into another, and then out of that one back, and then out of that one completely out of the system. So we call this tank, what we're interested in is the amount of salt in those tanks at any time. And we called X1 the amount of salt in tank A. So at time 0, it started with 25 pounds of salt in it. All right, and there were 50 gallons of water in each one of these. Okay, so the amount of water in each one started at the same amount. In the second tank, which we called X2, at time 0, there was no salt in it. Okay, there was no salt. It's clearly going to get some salt in it though, because even though we have pure water coming into this one, it started out with 25 pounds of salt in 50 gallons, which is a pretty high concentration of salt, and then it went out of that tank into B. So salt water is flowing into B. Okay, the question is, how is the salt changing in each tank over a period of time? So you can kind of see what kind of sort of industrial problem we might be looking at. I mean, we might first, whatever, it might be looking at saltwater distillation problems or things like that. That's exactly what this one is. And there are lots of, there's a, just near near Wilmington, there's a big salt distillation operation in Wrightsville Beach. So they're those kind of, I mean, water is a precious commodity, and we got lots of salt water, not a lot of fresh water comparatively. So if we can make fresh water out of salt water, that's a good thing. Okay, so so let's take a look at how we set it up first. We talked about looking at a rate of change. Oops, sorry, I'm going the wrong way. We looking at a rate of change. So in tank A, we talked about the rate in minus the rate out, and we had 0 pounds per gallon here in this X1. Remember, that's the tank into which the fresh water was coming. So there are no pounds of salt per gallon in that to begin with. Looked at all the concentrations of the rest of the tanks, well, X1, X2, and then we looked at what was going out. And if you remember, there was one line going out of A. All right, so that's right here, okay? And it was going out at 4 gallons per minute. And X1, after the process starts, we don't really know the concentration, so it's the amount of salt over the amount of water in the tank, or the amount of solution in the tank, which is A. All right. We did the same thing for B. B had places where one way the water or the solution was coming in, and the other situation, this line and this line, the water was going out. Okay. So so that's what, when we ended up playing out all these rates in and rates out, the system that we got was this system right here. Let's see, find it here. All right, it looked like that system right there. So the rate of change of the amount of salt was equal to this, involving tank 1 and tank 2. That was this, again, X1 was the amount of salt in tank 1, and X2 was the amount of salt in tank 2. Now, we didn't know how to solve that when we first started systems of equations. But what we knew was that we had 2 equations, and we had some initial conditions. I get more and more sideways the later at night I work. I don't know, when I look at this thing, I feel like I ought to pull my computer up 10 degrees. Anyway, we got this. Now, what we did on these problems, just to remind you, and this will be similar to the one you've got to work for homework. I'm going to do this one by elimination rather than determinants. I could not do it during you're using determinants. If it's a homogeneous system, if there's zeros on either side, you can see that if you were to put this line of something in a determinant, you'd get a 0 determinant in the top. So it wouldn't give you anything but perhaps the trivial solution. Okay, you use those, and this applies to the one in the homework. You did have non-homogeneous system in that one for the homework. I think it had maybe a 4e to the t and a e to the 3t or something here. You could use that. You could use determinants to do that one because it's non-homogeneous. All right, so the next thing we did was write it in operator notation because it was much easier to deal with like that, which meant putting the x parts together here. So x1 parts together in this one, and the x2 and the x parts together in, unless I didn't, oh well, I didn't put them together, but these two right here should have been together, right there, and then the x1. All right, so when I write them in operator notation, if you look at the first one, there's a first derivative, so it's d plus 2 over 25 with x1, and then minus 1 over 50 x2. If I look at the bottom one, if I put x1 first, it'll be minus 2 25ths x1, and then d, first derivative of x2, plus just x2, so d plus 2 25ths x2. So that's how I write it in operator notation. So whether you use elimination or whether you use determinants, you need to write it in operator notation first. Okay. All right. So questions, anybody, about how I got to that point? Does everybody feel okay with that? All right. I'm gonna use elimination here, and I'm gonna eliminate the x2 here. And you can write down the details if you want, or you can just sort of walk through this with me. Part of this is in the book, but again, it's not to the same level of detail. But I'm going to eliminate the x2s. So I'm going to multiply, look at the coefficients that are on the x2s. I'm going to multiply this one by the operator d plus 2 over 25. I'm going to multiply this one by the operator 1/50th. Fortunately, and I kind of like it when this happens, those signs were already different. So I don't have to mess with multiplying by negative an operator or anything like that. They're already different. And the point is to get one of them positive, one of them negative, so the whole works drops out. So when I multiplied by d plus 2 over 25, I ended up with a d plus 2 over 25 and a d plus 2 over 25 when I looked at the first place that I went here. All right, and the next place was the d plus 2 over 25 and the minus 1 over 50 that was already there. When I did the 1 over 50 here, all right, I reduced this, guys. I took minus 2 into 50 and got 25. So that's minus 1 over 25 times that 25 is 1 over 20 minus 1 over 25 squared. So I did a little simplification as I went there. Okay, so it was that times that. The other one was just 1 over 50 times d plus 2 over 25 x2. Nicely, that gave me exactly what I wanted to happen, that this thing would drop out. And when it dropped out, I got these two things right here added together. So you're adding that equation to that equation. That one dropped out the way I manufactured it to. Then that means the operator on this one is going to be d plus 2/25 times the d plus 2/25 from right here, and then minus the 1 over 25 squared. So this one is working out like all the other systems. It's not particularly pretty just because of these fractions in the operator. And those were concentrations basically, so that makes sense that they're going to be fractions. At that point, I tried to put all this together because I need a characteristic equation. That's what I need for this thing to work. And when I did that characteristic equation, I multiplied this out, and then 25 squared was 1 over 625. When I added things together, I got this, all right? I didn't like the look of that, so I cleared out the fraction in it, which I can do because I'm just multiplying two sides of the equation by the same thing. Of course, on this side, I'm just going to get 0. And on this one, I get 625d squared. All right, so I get 625d squared. 25 into 625 is 25 times the 4 is 100. And then the 625s, I get 3, okay? So what you're looking at right there is the characteristic equation. If I were to write out the actual equation, it would look like this. 625 x1 double prime plus 100 x prime plus 3x equals 0. Okay, now x is my function. X is a function of time. Okay, so what I see is a DE, second order, with constant coefficients. I need a characteristic equation. This is not a Cauchy-Euler thing where it's it's a little different coefficients. It's just the coefficients that appear on here. So I get 625m squared plus 100m plus 3 equals 0. Not terribly hard to see. Well, it is kind of hard to see. You could try and see what happened here, but it turns out that it factors. If it doesn't factor, use the quadratic equation on it, you're clearly going to get the same roots. So when I factored it, I got 25m plus 1 times 25m plus 3. So I got the 75m and the 25m gives me the 100 and 1 and 3. So it's not immediately obvious that thing's going to be nice enough to factor, but it does. Questions to this point, anybody? Okay, so what we know is that you've been working on this for all weekend for the test. You got this constant coefficient DE. You got 2 real roots. Okay, we know then that x1 is going to look like c1 e to the minus 1/25 t plus c2 e to the minus 3/25 t. So you know those roots right there, come down as these powers on E. Okay. Now I didn't do the work, but if you think about what happens when you do it with determinants, or when you would do it with determinants, it's over the same Wronskian, it's over the same fundamental set right here. If you eliminate the x's, x1s, you'll get exactly the same thing for the x2. It's not hard, you just multiply it by whatever you need to get the x1s to drop out. But you got to be careful here. And this is what I wanted to remind you of before you started working on the system that I gave you. They look the same. They have the same fundamental set with them, but their coefficients are not necessarily the same. So when you get x1, if we put c1, c2 on it, and we get x2, we're going to put c3, c4. Now, a word of caution on the one that I gave you. I think I gave you one. Well, no, I didn't give you the one from the book. Depending on whether you listed this root first or that root first, you could have had a C1 on this one and a C2 on that one, or you could have done this first. You could have eliminated the X1s and gotten the X2s, in which case this would be C1 and C2, and that would be C3 and C4. So the long story short, if you do some of these in the book, the C1s and C2s are going to be related in the same way, but your solution isn't going to look the same. All right, you'll be able to show it's the same if you want to, but it's not going to look the same. Okay, so let's figure out what we do next. The next thing we've got to do is write, and usually we'll do this. I mean, it doesn't matter which way you do it, but we're going to write C1 and C2. C3, I think I did, and C4 in terms of C1 and C2. Because I only have, I mean, if you think about it, guys, I only have 2 conditions. So when I plug those conditions in here, I need to be able to find all 4 of these things. So what we do next is this. We pick one of the original equations. And it doesn't matter which one. I picked the one that had to do with the rate of change of x1. So you pick one of them. The whole point is to plug in what you found out x1 and x2 are, along with the C1, C2, C3, and C4. And once you do that, you'll have a string of things that have C1s, 2s, 3s, and 4 in them. But because these 2 solutions came out the same, in a sense, the C1 and the x1 and the x2 had the same e to the minus 1/25th t and e to the minus 3/25th t. When you plug that in, you'll get all your terms will either have an e to the minus 1/25th t or an e to the minus 3/25th t. So I plugged it in, and here's what the solution looked like this, or when I plugged it in. I plugged everything into this. So that, guys, I looked at that thing right there was my x prime. And if you go up here and you look at, you'll see that. If you go up here and look at what x prime had, you're going to differentiate it. It's going to be e to the minus 1/25th t times minus 1/25th c1. So you're going to pull that down. This one, of course, will be c2 e to the minus 3/25th t. Pull that minus 3/25th t down and you'll get that. And then I put in the x1 right here. So that's x1. And it had gotten multiplied by the minus 2/25. And then, since I ran out of space, I got 1/50th and plugged in the x2. So that thing right there is the x2. Pick one of the equations. It does not matter which one. Doesn't matter which one of your original members of the system you get. You plug them all in. Now, this is where it gets a little bit messy. It reminds me a little bit of method of undetermined coefficients. It can get messy, but you just have to be careful. I multiplied everything out, combined what I could, and realized that because these things were equal to 0, okay? Again, I multiplied all these things out. What I did initially was group all the things with an E minus the 1/25th t. So all of these had this term right here. You could combine a couple of them because you had a C1 and a C1 here, so I did that. The other ones had the -3 25th t right there. So I put them all together, realizing that this e to the -1 25th t is never going to be 0. I can just pull it out, and then to make it look better, I multiplied through by 25. So that's never going to be 0. So the only way this thing's going to be 0 after I multiply through by 25, that'll make that a C1. Minus 25 over 50 is a half, C3. So that's got to be 0. You're kind of matching the coefficients of the e to the -1 25th t's and the e to the -3 25th t's. And since there's 0 on this side, their coefficients are always 0. The other thing I did was take care of the e to the -3 25th t. And again, I multiplied through by, I guess I multiplied through by 25. You can pull that e expression out. So I got minus C2 multiplying by 25 here, minus 1/2 C4 equals 0. Those are the two equations that are going to allow you to write C3 and C4 in terms of C1. Okay? So let's look at what I did then. That's perhaps the messiest part of this process where you have to plug it in and match the series. Now, I toyed with the idea of giving you a 3 by 3. You'd have to use determinants for that potentially, or some kind of elimination. It's messy though, because if you have 3 equations in say 3 variables, you're going to have C1, 2, 3, 4, 5, 6, 7, 8, 9, and you got a lot of legwork to go through to figure out what those are in terms of only 3 of the C1, C2, and C3, and so on. So we got other things to do. So, okay, so what I did, knowing this, from all of that work, I got this. I put those on here. So there was my X had the C1 and the C2 in it. The C3 was 2C1, and the C2 was minus 2C2. So now I've got the system solved, and I'm ready to use my conditions. Okay, now remember my conditions were that at time 0, there was 25 gallons of salt in tank 1. At time 0, there were no gallons, no salt in that X2 because it was full of pure water. So like I usually do, I'm going to put these conditions in. So there was my X1 right there. When I put in 0, I clearly get C1 plus C2, and that's because these E's are going to be 1, e to the zeros. And then 25 on that side. And then these are going to be zeros. And I'll get 0 on that side. I get this. Eliminating the C2, which was pretty easy to do. I mean, as a matter of fact, I just divided this one by 2 and then added the 2 together. I got 2C2 is 25, which meant that C1 was 25 halves. And since they both have to add up to 25, C2 is the same thing. So there they are right there. Okay. So this thing is solved. It'll tell me at any time how much salt there is in the tank. Okay. Now, I want to go back and look at the tanks and see if you can guess what's going to happen in the end to this system. And then I want to look at what would happen if we tried to sort of figure out what was happening in terms of looking at a graph. Okay. So I'm going to go back. Those are the solutions right there. Let's think about the system. You got pure water coming in here. You've got it's going into a tank with salt in it. You've got the mixture coming out here and then going back in here, and then you got ultimately this going in the end. Now, if I said to you, I want you to concentrate on the fact that the only new water coming into the system is pure water, and it's getting circulated back and forth and then going out, what do you think is going to happen in the end to the amount of salt in either tank or both tanks. What do you think is going to happen with the amount of salt there, guys? Anybody? Mic off. In the end, how much salt?
They're both going to be pure water at some point.
Okay, that seems like a reasonable assumption. Okay, so I think that was Allison. It looks like since you've only got pure water coming in, you had all the salt that was in the system to begin with was the 25 pounds that were right here. And so hang on, guys. I'm sorry, I got a phone call coming in. Shoot, hang on. Dad, hey, I'm in class, so I'll call you back later. Okay. Are you okay? No, I can't do that. I'll talk to you later. Bye-bye. Okay, I'll talk to you later. Okay, bye-bye. Okay. So I think Allison's right. I think essentially you're going to get this continued dilution of the water in here, of the salt water, and you're going to get fresh water. So guys, what I want to do right now is I'm going to temporarily unplug what I've got right here to share with you. I'm going to try to put on a calculator. All right, and this worked last night, so I hope it's going to work right now. And I'll show you what I've got. So hang with me for just a second and see what happens. Okay. Let's see. Okay. It's kind of paused, but I've got. Can you see what's on the screen? It's paused. Hang on one second. There we go. I'm having trouble getting the picture up. Can you guys hear me? Let me know if you can hear me.
Yeah.
Okay.
Yeah.
I'm trying to get this up and shared. Can you see the calculator?
No.
No? Okay. It's not sharing properly. Hang on a second. Let's see what I can do. I think I've got. I knew this would work one time and it didn't work now. It's gonna make me mad. It doesn't trust my computer for some reason at this point. And I get that out. Okay. Well, let me tell you what I've got and see if I can make one more attempt here. Back to here. What I've got on this thing, it's a T. What you should be looking at, and I don't know. Let me check News Share and see what happens. Ah, there we go. Let's try that. I bet that'll work. So do that and do that. All right. Can you see anything now? You see the calculator now by any chance?
I still can't see it.
Ah, okay. This is making me mad. What I have up here is a simulator for a TI. And what I've done on it is is put the two equations into the calculator, just like you would just put it into your calculator, although I mean, it really works really nice here. I'm trying to hit resume share, but it keeps asking me, it keeps telling me it doesn't trust it. I'm gonna plug in the other one first again and tell it I trust it. What happens? It's a different share. Okay. All right. You see anything now? No. You see where I was back to, but I'm gonna try this one again. All right, I'm gonna close it back down and try one more time. This is too bad because I really like this picture that it had. I'll cut that off. Definitely trust this computer. Do that. And come back to that. All right, I'm gonna try one more time to go back out of it and see what we got. Now to go back out of it, I have to unplug this one. So let's see what happens again. Same old crap. Okay, let's see what happens. All right, there's the calculator. There it is again. Tell me if you see the calculator, but I have a feeling you don't yet. So I'm gonna hit new share. And I'm gonna go with this and this. All right, I can't get it. I can't seem to get it up. Let's try this one more time. That one. Anybody see it? No.
I see a calculator.
Okay,
Calculator.
excellent. Okay, so everybody see the calculator? Everybody see it?
Yeah.
Yeah, okay, good. All right. So what I did on the calculator was I put in those two equations that gave me the actual solution there. And I had to, instead of using x1 and x2 and t, I had to make x the independent variable, which would have been time. And y1 and y2 were the two tanks, all right? So I also put in a window that I thought would work with what I wanted to see. So if you'll look at the window that I've got, the x max, I put on it as 100, then that again is time, x is time here, and y is the amount of salt in any tank. So I put the y max as 30 because I knew the most salt that had been in it at any one time was simply the 25 pounds. So I'm gonna graph this thing, and so look at what's happening with the graph. Well, it was nicer when I had a bigger screen on it, but that's okay. The blue one was tank 1, guys. And what happened here when I put my scale on this was in twos. The scale was in twos. It had 25 pounds right at the beginning. And then it started to cross here. This one went up for a while. It had to because it was pure water to begin with. And so the salt concentration went up for a while, and then it came back down. At some point, at some time, and that's the independent variable here, at some time, they had the same amount of salt in them. So if you wanted to find this from your information, the information that you had, you would have had to set those two equations equal to each other and solve for time. It's not particularly hard to solve, but it's a little messy. It's nicer to see it sort of in the graph, I think. Now, suppose I wanted to know what time that happened. And also notice that Allison's conjecture that both of them were going to go to 0 salt, okay, and that's what the y-axis is measuring. They are both approaching 0 salt as time goes on. So if I look at the trace and move the trace over to the intersection point and look at the bottom, you'll see what the y is. Remember, the y is the salt, and I hit the intersection point as close as I can there, and it looks like that the time where the salt in the two tanks will be the same will be about 13.5 minutes. I think this was all in pounds per minute and so forth and so on. Or was it second? I think it was minutes. So what you've got is at 13.5 minutes, roughly, the 2 tanks will have the same amount of salt in them. And the amount of salt that will be in them is 9.7. Okay. Let me try something else. I had a larger picture of this. Does everybody see what's going on there? It's nice sometimes to see what's happening from a visual point of view. And I know we haven't done a whole lot of that because we've sort of been stripped of what I usually do with Maple for the last half of the semester. I think the only thing we got to do on Maple was those direction fields or slope fields that we looked at. But anyway, it works fine on the TI-84. You can see it. The newest TI-84 that they've got out is called a CE, and it can, if you look at the Y equals on these things, you can do every one of the Y's you put in a different color. It'll display in a different color. It's really nice. And then the graphs will display in a different color. So it's a nice one. Does anybody have a CE? I was working with an 83 that was old as the hills, and then I went to a conference and saw this thing, and I'm like, I might have to have one of those. So that's a simulator you can load up from the TI site. Okay, questions, anybody about that? Okay, so what I'm gonna do right now is go back to, I'm gonna quit this. I'm gonna go back and share my other window and share my iPad again and then talk about something else, okay? All right, there we go. Okay, questions anybody about systems? Because that's about the last thing I'm gonna say about systems. Okay, so let me go back to I'm gonna do an introduction to Springs today, and maybe remind you of some things that you've had before. Let's see if I can get what I need here. I gotta get all the way back into the program here. There we go. Let's go back. Okay, so let's see if I can find my Springs here. When I look at all I've done and you've done over the semester, when I look at this, I'm like, wow, that's a lot of stuff. Somehow when you get it all in one place, it looks like a lot. I want to introduce today some of the ideas about Springs. Okay, so this is chapter 5, and it's this application on Springs is done in actually 3 different sections. The first one is has to do with undamped motion, and that's what I want to just introduce today. And we'll come back on Wednesday and talk more about it. So these are applications of second order Ds with constant coefficients. It's basically springs and just simple harmonic motion. Now, the way we set these things up is going to have an effect on sort of how we view their graphs and so forth. So let me just sort of look at what we're doing here. Basically, what we're going to have is a spring. There's my lousy looking spring attached to a rigid support. So there's no sagging with the support or anything. And that spring, if I just let it hang, we'll just say it's unstretched and there's no weight attached. I'm not pulling it. I'm not putting a weight on it. I'm just leaving it there. It's the spring as it is in its unstretched form. Or compressed. We can also compress springs. Springs go up and down, so they compress and lengthen. If, on the other hand, I have it on the same support and I put some kind of mass on the end of it, it's going to move down. All right, gravity's going to pull it down. That right there, guys, is an S. All right, so the distance that the mass pulls the thing down is S, and that's beyond its natural length. And L is what we're going to call its natural length. Okay. Now, those of you who took Calc 2 here, sometimes depending on who you have, they skip some things in the work section. And one of the easiest types of work that you got to do was something that talked about how much work was done by stretching a spring. And what we needed to do that is a law from physics called Hooke's law, okay? And Hooke's law basically says this: the spring exerts a restoring force in the opposite direction of the elongation and proportional to, that word didn't get in there, probably because I misspelled it the first time, proportional to the amount of elongation. In other words, if you pull that spring down, you're going to have forces acting in the direction you're pulling it down, and the spring, if you let it go, the spring's going to want it to come back up. So you've got these two forces working in opposite directions. And what Hooke's law says, and this is one of those laws of physics that they figure out by observation, essentially. Springs have different, what we call spring constants. Some springs are harder to pull, some springs are loose. So we've got this thing called the spring constant that describes any particular spring. And the force, and this is the idea behind Hooke's law, is just K times S. And S is the amount of elongation there, where K is called the spring constant, and it's in foot-pounds or pounds per foot, kind of the force here. So it's F equal KS. Probably in Calc 2, you saw it as F equal KX, and you said how much work is done in pulling the spring from 2 inches beyond its natural length and 5 inches beyond its natural length. We would do problems like that. So let's look at a simple problem using Hooke's law. Suppose we've got, and I'll leave it up there, a mass weighing 128 pounds stretches a spring 2 feet from its natural length. Well, the 128 pounds is the force in the system. So we set that equal to 128, and that's going to be K times 2, because 2 is how far we've stretched it beyond its natural length, okay? And we end up with K being 120, that's not an S, sorry, there should not be an S there, right there. Well, never mind, let me get rid of that. That says K is 64, just dividing both sides by 2, and then that means the force function there is 64 times S, okay, because there it was. F is KS, we determined K to be, and we could compute the force constant or the spring constant from any amount of elongation. That's gonna be what's true for that spring. So F is 64 times S. I mean, has anybody done springs either in physics or Calc 2? I mean, who did it? Who's done it in Calc 2? It was in the work section in Calc 2. Unmic and tell me if you've done it if you remember springs in Calc 2.
I
Kind of remember it.
Yeah, okay, Sylvia, you don't remember it. Ella, did you do it in your AP course in high school in the BC, I guess?
I don't remember.
Okay. Anyway, how about your physics courses? Did you do springs in your physics courses? Anybody?
Yeah.
Okay. So probably they do springs in harmonic motion in physics. I'm going to give you kind of the mathematician's view of it. A lot of times in physics, I shouldn't say this. In my physics class, at least, there was a lot of hand waving about the math, and I was like, well, whoa, wait a minute. Show me the math. And it was a lot easier for me to understand if I could see how the mathematics worked. So let's look at what this essentially means. It says the weight on the spring is the downward force, all right, versus the upward force or restoring force exerted by the spring. That was that sort of up and down competition of forces there that I'm just talking about. Now, let's talk about units for a second. Weight is equal to mg here, and one way to look at that, the weight is your force here, and it's mass times acceleration, and this g is acceleration due to gravity, right? So if it's a mass, it's measured either in slugs or kilograms or grams, this being the English unit. If you use the English unit, and you'll need this for certain problems because they sometimes put it in different units. If you're looking at English units, your gravitational pull is 32 feet per second squared. Typically in science books these days, they say, you know what, why are we just dragging along behind the rest of the world using feet per second? Why don't we use meters and centimeters and so forth? And they've got a point. You know, the English system was really sort of a system set by basically the kings in England. And the story goes that a yard, people decided on what they wanted a yard to be based on how far it was from the king's nose to the end of his outstretched arm. I'm like, okay, well, that seems blatantly unscientific. Basically, we usually see things in meters. And I would hazard a guess in your physics classes, you would see them in meters. In the mathematics classes, on the other hand, sometimes they just leave this at 32 feet per second squared. Okay, I think in the calc book, they almost always do this instead of meters for whatever reason. I don't know why. Okay, so let's look at some ideas here. We say the system is in equilibrium when mg. Now remember, mg was the force in the system due to the weight being hung on this thing, and ks was the restoring force of the spring. That was the spring constant. That's due to the spring. That's due to the weight on the mass hanging on the end of the spring. So what we've got here is that we say the system's in equilibrium when these two are equal, and just moving the ks over when mg minus ks is equal to 0. Okay, so keep that in mind because we're going to use that in a minute. So I got 3 situations here I want to look at. The support without the mass on it, the unstretched spring is L. If I stretch it S units, there's S units beyond the original length. If I then say I'm going to pull it down further, I'm going to let that value be X. Now, here's what happens in spring problems. If it's in equilibrium, say, you know, maybe you're looking at this picture right here, in a sense, with the mass on it. So it's sort of stopped. The spring is sort of stopped. The weight is pulling, the mass has no more, you can't pull it down any further, and the spring can't pull it up. You're sort of in equilibrium here. But if we want to set this whole system in motion, we may take whatever that mass is and pull it down and maybe give it an upward force to get the spring going up and down. Or for that matter, we could pull it up over here and lift it up and then let it go, and you get some motion that way. So this X can be talked about how much I pull it down. Okay, so let's look at that. So we're going to displace the spring by X units. The restoring force of the spring is now F equal K times S plus X, because our elongation, our length now beyond the L is S plus this additional X. Okay, so that's the restoring force there. Now let's talk about one of Newton's laws, and then I think we can get something going. Newton's second law of motion. Looks like this. It says the net force acting on a body, that means all forces put together, in this case would be the mass pulling it down, the spring pulling it up. The net force acting on a body is equal to the time rate of change of the momentum, and by momentum, Newton meant velocity of the body. So net force F is equal to the time rate of change, velocity times m, times whatever the mass is. Now, if X is the equation of motion, in other words, where is the spring at time X given a certain time, then the derivative of velocity, well, the derivative of X, one derivative will be velocity, 2 derivatives will be acceleration, or the second derivative. So there's the law, F equal mass times acceleration, F equal ma. Okay. Now let's talk about what we've got then. That's what Newton's second law says, is that this entire amount of force right here is equal to the weight of the object, all right, pulling down, all right? It's working with gravity minus the restoring force of the spring, which is pulling against gravity. That's the minus right here, okay? So that's the equation that we get. So again, right there is the weight of the object. Right there is the restoring force of the spring. It's the total, the net force in the system, okay? And this is F equal ma. That's Newton's law, Newton's second law. Okay? Now, here's what we're gonna do. And we're getting close to an equation here, guys. Because typically we'll know the mass, we'll know whatever gravity is in that particular situation, we'll know how much we pulled it down, we'll know how much the, remember S was what the mass pulled it down, and then there's the additional amount that we pulled it down. So we're gonna assume something that's not very realistic, but we're gonna start with the easiest case first. We're gonna assume that there are no retarding forces acting on the system, okay? And the mass vibrates free of other external forces. Later on, we're gonna look at what if we've got a machine driving this thing, all right? That would be an external force. Or what if we put this underwater and the water was causing it to have what we call a damping motion. What we're talking about right here when we have no more retarding forces, or no retarding forces at all, is called free undamped motion. Okay, free undamped motion. So putting in the things that I have here, I'm gonna look at this equation right here. And you see it's the same one I had up here, but all I did was multiply out that minus kx and minus ks and kind of change the order here, right? Where when the system is in equilibrium, remember that mg minus ks is equal to 0. Okay, so when it goes through equilibrium, this is what's true. So what we're gonna do here is say, well, okay, well that's true of this system. And I'll take the mg minus ks, and that will be 0, okay? Which only leaves me with this. Once again, the m is the mass attached at the end of the spring. The k is the spring constant. Now, let's move everything over to one side. I want to move this kx over here, and then I'm going to divide by m. You can see what I'm doing here. I'm making my differential equation. And the k over m, again, spring constant over the mass. I won't say just physicists, but mathematicians kind of like for things to come out nicely. So they name things, variables that will make them come out nicely, and remember that they were actually in the beginning this. And in some of these problems that you're asked to work, you're given the mass, you're given the spring constant, and you'll form this thing called omega squared. Okay? Now, we only square, you say, well, that's omega is the square root of k over m. And I'm like, yeah, that's fine, but that's ugly. So we're just going to call it omega squared. And you'll see why in a minute based on what the solution to the DE will look like. So all the way through the problem, I know omega squared is going to be k over m. Okay. This is an equation for what we call simple harmonic motion. It's a second order DE with constant coefficients. I know how to solve that. So let's look at sort of the setup here, and then we'll look at it and then see what we got here. The support is right here. X, guys, we're gonna let X, seems a little backwards, but if X is less than 0, remember X was the amount we pulled it down or pushed it up. If we pulled it down, the spring is longer and it's below equilibrium. We're gonna say X is bigger than 0 when it's below equilibrium because we pulled it down a positive amount. By pushing it up, when it's above equilibrium, we've shortened the spring and we say X is less than 0. So this is gonna be important to us when we set these things up. X is less than 0 means it's above equilibrium. X equals 0 obviously is right at equilibrium. Below equilibrium, X is going to be bigger than 0. Now, in order to solve these things, we're going to have a couple of initial conditions. We're going to say x of 0, that is its position at 0. Now, guys, what I'm aiming for here is to solve for x of t. And that x of t is what we call the equation of motion. Okay? So here we say x of 0 is x naught. That's going to be the initial displacement. In other words, at time 0, it's where this spring was. That was its initial displacement. How much did I pull it down before I pushed it up or did whatever I wanted to do with it? If x0 is less than 0, if x naught is less than 0, we're starting above equilibrium. Remember, if I said if the spring got compressed, that would be less spring, so it's less. If this x0 is bigger than 0, it means we pull it down. We've pulled it down. Okay. The other that's the initial condition for position. This is the initial condition for velocity. It's the initial velocity. So if x1 is negative, or if the initial velocity is less than 0, then that means it's imparted an upward velocity. Now it's acting against gravity. That's why we say, well, if we take the spring and it's got the mass on it, and I take the mass and I push it up, it's working against gravity, and that means x1 is going to be less than 0. It's going to be negative because we'll have a decreasing function essentially. On the other hand, if x1 is bigger than 0, all right, it means we put, and now this should have been a 1 right here. If x1 is less than 0, it means we pull it down. It's working with gravity when I pull it down. Long story short, there's the dE right there. Okay, you can kind of see why I made that omega squared, because if I look at the characteristic equation for that thing, it's going to be m squared plus omega squared. Remember how we just picked off the coefficients for the characteristic equation. Now, let me say something about this m. Because we're in a physical situation here, and m typically stands for mass, you will often see them putting r's in their characteristic equations. Okay, and we kind of know contextually that m is not mass. It's just an equation we need to solve this dE. Now, if you solve this, if you solve r squared or m squared plus omega squared, move the omega squared over to the other side. It's a positive number. And you move it over, it becomes negative. Take the square root. You're going to get a negative under the square root. And then m, the roots of the characteristic equation are m equal plus or minus omega I. And that's why we didn't leave k over m in here. We really kind of wanted a prettier root here, basically. So again, what I'm doing here is solving for r. It's going to be the square root of minus omega squared. I get the I, and the square root of omega squared is just omega. Okay, and I get, of course, plus or minus. What do we know about that? We know that's an imaginary number, a complex number with a real part 0, so I get e to the 0t. And the omega is the imaginary part, so I get cosine omega t plus sine omega t. That is what we've learned, and you're used probably somewhere on your test. Okay? So we get x of t is c1 e to the 0t, cosine omega t plus sine omega t. Okay, let's see what that tells us. Couple of things going on here that you'll be asked about. Let's define the period. The period of free vibration depends on what that thing is right there. So a period is just going to be 2 pi over omega. It's 2 pi because the typical period of cosine and sine is 2 pi. So you might remember this from trig. We're going to be doing a fair amount of trig here. If I had the cosine of 2x, and if I compared it to the cosine of x, that's going to have a period of 2 pi. It takes 2 pi units to get cosine all the way around the unit circle, basically, is what it's saying. 2x speeds things up. Things happen twice as fast. So if you look at, it says 2 pi over, that would be my omega there, 2 pi over the 2 that is there. That means that the period of that one is pi. So it happened twice as fast. Period of this one's 2 pi. But that's the formula we use to find what the period is. That was a standard thing in trig. The frequency, you probably didn't talk too much about in trig, but you may have talked about it in physics. It's just 1 over the period. Okay, that's all. And basically it says the amount of times a particular motion is going to happen in the length of 2 pi units. Okay, so here's what I'm going to give a quick example, and then we'll come back and talk about this on Wednesday. Suppose and I'll just give you some things we'll look at to find. Suppose you've got an equation of motion, and you don't know how well, you do know how to, we just found one, but we hadn't answered any questions about it. But suppose I gave you this one right here. Okay. The period of this one is 3t, so things are happening kind of 3 times as fast as they normally would. The period will be 2 pi over 3. That means the graph of x of t repeats every 2 pi over 3 units. Okay, the period looks like that. The frequency is 3 over 2 pi, and essentially that means there are 3 cycles of the graph every 2 pi units. So 3 cycles per 2 pi units is what that means. Okay. Couple of words we'll come back and work with later. The maximum displacement is displacement we talk about when we say below the equilibrium. Okay, below equilibrium when we pull it down. Minimum displacement is how it's really sort of looking sort of at the length of the spring in a sense. But it's where the spring is at any time. It's been pushed up, so that's the minimum displacement when it reaches that top point right there. So that's minimum displacement. Later on in these problems, they're going to ask you for extreme displacement. What they're asking for there is both the maximum and the minimum. If you remember from Calc 1, when we were asked to find absolute extrema, they wanted 2 things: absolute max and absolute min. Same thing here. If they say I want extreme displacement, I want to know how far up or above equilibrium it is and how far below equilibrium it is. Okay, real quickly, let's look at what this thing looks like, or an example here of what might happen. This is just another example. It's not connected to the last one. Suppose we had this was our equation of motion. We had m squared plus 16. That means omega squared is omega equal 4, and I should put omega is plus or minus 4i essentially, because you're solving m squared equal minus 16. When I take the square root of that, I'll get plus or minus 4i. These things right here are my initial conditions. At time 0, you get a positive number. That means you have pulled it 10 feet below equilibrium. So you've stretched out the spring there. The fact that the derivative is 0 at time 0 means that you don't give it a push, and you don't push it down, or you don't push it up. You just let it go. You do not impart any velocity to it. You just let it go, and it takes care of itself. Okay. All right, so here's my dE, because the e to the 0 t is because the part of this is that. And we'll get C1 cosine 4t plus C2 sine 4t. That's my equation of motion. These conditions will allow me to find C1 and C2, which is what I did. We know that if you plug in 0, you get 10. If you plug in 0, the sine drops out. Cosine of 0 is 1. That means C1 is 10. If you take the derivative, which I did, I just took the derivative of x here and plugged in 0, I should get 0 from that initial condition. If I plug in 0, anything with a sine in it becomes 0. The cosine is 1, but that says 4C2 is 0, which means C2 is 0. So wherever this equation of motion came from, I end up with putting my C1 here as 10 and my C2 as 0. My equation of motion looks like that. Okay. So, and there it is right there. If I want to find a picture of it, this is what I'm going to draw. I know that this line right here represents equilibrium. The axis itself represents equilibrium. Okay. We said it's maximum displacement being positive, that it's at 10. So x of 0 is 10. If I look at what a cosine's doing, whose period is pi over 2, and I found the period by putting 2 pi over 4, then it does one whole period in between there. I know what a cosine does. It cuts the axis a quarter of the way through the period. Halfway through, it's down at this minimum value here. This means the mass is below equilibrium because I've stretched it out 10 units. That's what that's all about. The extreme displacement when it's above equilibrium is also 10 units. Here's how you can find extreme displacement, guys. You want to know when the derivative is 0, because that's where the horizontal tangent lines will be. That's when it stops going up and starts going down again. All right, and again, it seems sort of backwards when you look at the picture. But if I take the derivative here and find out where it's equal to 0, I'll find all those places I said before. In between here at t equal pi over 4, there's another one that we're not going to look much further beyond one period, but there'll be another one at pi over 2. This would go back this way. There would be another one at 0. And that's what that equation of motion looks like. And it's just going to keep doing that on and on and on. That's not very realistic. Most springs don't do that. Okay, they start to slow down. Okay, that's all I want to say today. Wednesday, we will start with an example, another example to carry through with this thing to find the equation and solve it and look and see what the picture looks like. That I'm hoping I'll be able to get my calculator program back up a little easier to get to. And bring your calculators, because it'll be nice to be able to put these things on there and look at that. They're nicer pictures on Maple, but we can get by with a calculator. You only have one problem to look at in homework, and it's like basically find a spring constant for this system. So there's not much to do there. What you've got for Wednesday is one system of equations to solve and one nonlinear equation, and that's it. Questions, anybody? Okay. I will talk to you on Wednesday. Get me your test sometime today, and I'll start working on those. I'll see you later, unless anybody's got another question for me. Everybody okay?
Yeah.
Okay. All right. I'll see you later. Bye.
Bye.
Bye.